All right. I think this is working. I have concurrent viewers. I have slides. I'm here on the road, broadcasting live from my hotel room with no audio. No audio. Well, what do we think about that? Okay. Audio there. Oh, all right, good. I was at that point where I was about to panic. all options already having been implemented. I didn't know where we were going with this. Excellent, excellent. All right, today we're talking about stacks and queues. We're going to talk about some containers, and at the end we'll wrap up with a little discussion on generating permutations. We got a couple of pictures here that are a little bit descriptive. Here we've got Pringles, which I have been informed also contain potatoes, but they're a chip-like snack that come in this tube and they're stacked up. Get it? Get it? Stacks. And then on the far side is something that's probably before your time. Oh, we got nothing over there. Okay. That's good. That's good. It's good to get me going there. Let's try that. How do you like them apples? All right. I think we're good now. We got audio, we got video, and Pringles. Okay, on the far side is something that's probably before your time. It's called a Netflix queue. Netflix used to specialize in mailing DVDs to houses, and you would put this whole queue of things that you would like to see, and as they got copies, they would ship them to your house. You'd watch the DVD, you put it back in the envelope, and ship it back to them. That was Netflix's original business, but it was all centered around this queue here, and thus, of course, we talk about stacks and queues. We're going to start with our discussion about data structures and abstract data types, try to clarify the distinction between those two things. When we need some way to store and organize data, we generally try to define something, and we use what's known as an abstract data type to do this. An abstract data type encompasses the data that it's going to hold and any list of valid operations and how they behave on that stored data. For instance, insert, delete, some controlled way to access data inside of the container or collection. So we think of ADTs as defining an interface, whereas a data structure is a concrete implementation of an abstract data type. So the ones that we're going to talk about today is the stack abstract data type, and there's a very similar behaving stack data structure that's provided by the STL, and that is an implementation. So that's an implementation of the abstract data type, which is the interface and tells you how things are going to work, and then the STL stack does the work. As we look at all of the things we do this semester, we're going to be putting things through some performance hoops. We're going to have memory performance. We're going to have time performance considerations that are going into these things. And most of the things that we look at, we're going to look at how do we implement this? When we implement an abstract data type, when we turn that into a data structure, there's usually two primary choices there. We've got contiguous data. This is the things that you're used to in C-style arrays or C++ vectors. By contiguous, I mean all of the data locations are next to each other in physical memory. Or we've got connected data structures, which is where we use pointers like linked lists, or some tree implementations use pointers. So in that case, all of the memory that's used by a particular implementation might not be next to each other, right? So the connected doesn't mean that it's connected physically. It means that we've got some connection method to jump from one location to the next. This is generally pointers. Other things that we look at while looking at performance, we'll be looking at measuring runtime speed and the size of the data structure as we look at how much time is needed to perform an operation. We'll start out by using the step counting method, and once we get past step counting is a good way to fall back on trying to figure out how something works. Once we get a little bit past that, we'll be able to look at some more familiar structures, some familiar code patterns, and be able to get our performance by looking at that as opposed to counting execution steps. Other things we look at while measuring performance is how much space is needed to perform an operation. Can I perform the operation in a constant amount of space, or do I need to make a full copy of the object that I'm working on or the data that I'm working with? Do I have to do that? And then as we look for the real things that make performance important is how do these time and space considerations change when the number of items or the size of the data that I'm working with grows. So the number of inputs or the number of objects that are stored there. We'll do this with complexity analysis, and that's going to be a focus of a shortly upcoming lecture. I think I'm going to get into that tomorrow, or at the very least early next week here. So here's a quick one. Let's just look at how analysis works here. How many operations are needed to insert a value at the end of this singly linked list? So we've got a head pointer here, and that pointer points to one of my data elements, one of my list elements, or a node. There are a lot of different ways we can refer to it, but in this particular example, we see that there is a data item there. That's that one, and then the next portion of that node is a pointer. So this is connected memory. You see I've got this linked list that goes from 1 to 3 to 6, and then at the end of the list, the 6's pointer goes off to a null pointer and does not further extend. So let's look at how many operations are needed to insert some value at the end of this list. Well, we'll start with sort of accessing this first node. Then I check to see if it has a null pointer. If it doesn't have a null pointer, then I can access the next node. That's step 3 there. I check to see if it has a null pointer, because if it has a null pointer, then I'm at the end. I'm ready to insert. But it says it's not null, so that leads me to accessing that third node. So that's step number 5. While I'm there, I can check to see if its pointer is null. It is, so I found my actual insertion point. Then I've got to create the node that I want to insert into the list. I'm going to put the data value in that node. And finally, I'm going to update the pointer from the node that has the 6 in it to point at the node that has the new value in it. So there's my 9 steps that it's going to take for me to insert something at the end of this list. Right? The next question is, can I generalize this for a list with n elements? Here we said that it took us 9 steps to get something into this list of size 3. How do I generalize that for n elements? And if you look at this, you'll see that we've got an access and check step on each one of these nodes. And then we've got these 3 steps, which even if my list was empty, I would still have to create a node, insert the value in it, and then update my head pointer to point at it. So I'm always going to have to do those 3 steps there. You can think of that as some constant amount of work that has to be done. And then the variable amount of work looks like I've got 2 steps to be dealt with for every one of my nodes that's already existing in the list. So I end up with this 2n plus 3 operations to insert something at the end of the list, and I'll say that this is linear. This is important. We'll be looking at the fact that this is linear, so I can say that this has got linear behavior. I feel like if I double the size of my list, I can then roughly expect to double the amount of time that it takes me to do something. And that's what linear is going to tell me. And we don't worry so much about the fact that this is a 2 times n plus 3. Those are coefficients and constants that don't matter much. What really, really captures the behavior of this is the fact that it's linear. It's controlled by this n that's in the operation count there. As we try to choose data structures for a particular application, we're going to be looking for a few things. For starters, I've got to have it with the right operations. Can I add and remove things if I need to? Kind of fundamental. If I can't put the data in there that I want, or I can't get data out that's in my way, then that's not going to be a good data structure for me. Once I've got that, I also need to make sure that I've got the right behaviors. So as I add something, does it put it in a place where it should? Does it put it in a, you know, an arbitrary location? Does it put in a temporal location? Does it put in a physically related location? So I'm looking for the right behaviors. Can I push something at the back? Can I pop something from the back? Can I push something at the front or not? As I move forward from there, I'll be looking at other trade-offs for runtime complexities. When I do this, it's something that I do very rarely. So if my data structure is really good at it, I might be wasting something. If the behavior or the implementations that I use, or the things that I do happen much more frequently but aren't as well implemented. So we have to have these trade-offs between how often we're going to do something and how well it works. And of course, memory overhead is always going to be important when we're trying to figure out how much space something takes. So as we choose our data structure, we're going to go through this a lot. And those are going to be questions that we get asked a lot. And most of the time we're going to answer with, it depends, because almost always it does. As you look at multiple choices for what I can do to implement something, should I use the vector? Should I use a linked list? Should I use a Deque? Well, each of them have their very important advantages, and they all have disadvantages. And so that's why it's going to look like it depends when you ask a question like that. And what you're going to be learning throughout 281 is how to answer those it depends questions. We've got some potential concerns as we picked our data structures. We want to limit interface a lot of times so that people can't do things that would destroy the integrity of the container. For instance, if I've got a priority queue, its job is to give me the most important item. We'll talk about priority queues in a minute, but you can understand getting something that's the most important. So if that container allowed people to just change the priorities of items without telling the container, then that might cause problems. So that's a situation where you limit the interface. I don't want to allow the user full access to all the items because they may be able to break some invariant and then destroy how the data gets used. So some examples here is, what about order tracking at a fast food drive-through? This is an example of something that works like a pipeline. You come in at the back, the orders come, and they get passed out the window to people as they move their way to the front of the line. How do interrupted phone calls to a receptionist get handled? Think about what type of data structure might be useful for a receptionist dealing with a phone call and a new phone call comes in. How do I organize those? How do I retain them? How do I give them some ranking? How about to-do lists? I always like to think that to-do lists should be a constant size. So then if somebody gives you more work to do and your to-do list is already full, overflow happens and the object just goes away. It's responsible, isn't it? All right, so this is abstract data types. We talked about them as not implementations. They are interfaces. An ADT is a way that we think of things happening, and then a data structure is a way that actually gets it done. Those are our concrete implementations. Next up, we'll talk about a basic container that we've already alluded to already, and this is the stack. Stacks are something that we do use in our everyday life. I just had a stack of French toast. We got a picture down here with a stack of pancakes. But if I look at the abstract data type here, the interface, what are the commands that I can expect the stack to implement? Don't have to worry about how they're implemented. We'll talk about that separately, but what I'm going to do from a high level is just figure out what behaviors are available to someone using a stack. And stack, they support this insertion and removal in what we call last in, first out order, or LIFO order. Last in means the last objects that get put in are the first objects to be pulled out. Or if you are at a restaurant and there's a stack of plates, the most recently placed plate on top is the first one to come out. That's the last one on the stack, is the first one off the stack. So LIFO and stack are synonymous, and we'll just pronounce that as LIFO, and that means last in, first out. So we've got these five 5 basic methods, and when you implement a stack, you may implement additional methods if you choose to. But at the very least, if you implement them, someone that is looking at this as a stack ADT is going to expect these 5 methods. We've got push, which takes an item and puts it on top of the stack. We've got pop, which removes the top element from the stack. Just removes it, throws it away, destroys it if it's an object. The next one is this object reference to top. Keeps the item in the stack, but gives a referral back to it. So that can be used to print it or do any other computations with it. It can even be used to change the value here if we've got a non-constant reference that's passed back. Size is a way to count all the items in the stack, and that can be done depending on your implementation in a constant amount of time. It could be done in a linear amount of time, hopefully no longer than that. You're doing something horribly wrong if it takes you more than linear to count things, but that's an implementation detail. And lastly, something simple as, is this empty? And this is great because if you pop and it's empty, you can expect bad things to happen. Some examples of stacks are the web browser's back feature. As you do some surfing and you want to go back a few pages, that is a stack because the most recent page is the first one that gets moved off of. And then as they get older and older, they get farther back or farther down in the stack. A lot of times we'll draw stacks in this vertical way where we think of stacking things on top of them, just like the name sounds. And then as we stack something on top, this is the first thing off, and then this thing comes off, and this thing comes off, and so on. So that's how that works. An undo feature in any editor is a stack because it takes the most recent change and removes it. Function calls, of course, we use the call stack for dealing with the way execution happens. So those are some examples of stack. Now let's look at how we might implement it. So I talked about our 2 implementation methods, our connected versus our contiguous. So we'll start out with our contiguous. This is implementing a stack with either an array or a vector. One way we can do this is we keep some pointer, in this case it's called top pointer, and that's pointing just past the last element. And this is the STL style. I've got a base pointer there, which is pointing at the bottom of the stack. And then the top pointer is pointing just past the last element. And what that allows me to do is I can always write as soon as I want to. I just take that top pointer and write there, and then I increment the top pointer. So you can always think of the top pointer as not pointing at data, but always pointing just past the last bit of good data. So as I look at my 5 methods from the interface, if I want to figure out how I would implement them with this particular setup, you say, well, push. When I go to push an object, I know that I should be able to write at the top pointer. So I do have to check to make sure that I haven't exceeded the capacity of my container, and that's, I've got to keep my size somewhere separately. So here I can say, it looks like I've got 5 in my capacity and only 3 in my size, so I don't have to allocate more space. I should be able to just jump right to step 2, add a new element at top pointer, and increment top pointer. If it's needed, though, if I had only 3 capacity, or if I had 5 size to go along with my 5 capacity, my top pointer would still be pointing just past good data, but would also be pointing outside of my contiguous memory space. So I would say now, as I go to do a push, I need to reallocate. I need to get some more memory. In this case, I might say, let's go get 10 more items worth of memory. I'll copy the first 5 items into that 10 items, and then I can start inserting there with my push. To pop something, to remove it, I need to decrement the top pointer, which just means move that pointer back. And if I've got objects in my container, then I would need to call that object's destructor. How about top? This is to say, give me a reference to that top item. All we have to do is dereference the top pointer -1. So we move that pointer back 1 and send back that reference there, dereference that object. Size, of course, I can subtract the base pointer from the top pointer. That'll tell me how many items are in there. So size versus capacity. That's something in this particular implementation, we haven't said how much capacity we have. And that was one of the things I mentioned, is that's optional. You may have capacity as a check that you might offer the user, or you might not. Depends on what you feel. And lastly, I want to know if I can do empty. I can check to see if the base pointer is equal to the top pointer. Pretty straightforward. So the bottom question there, how many steps are operations for each method? Steps like write something, add to a pointer, dereference a pointer, something like that. So if I look at this, I can see how I might classify the time complexity of these operations. And I believe I've got a summary slide of that, so I'll come back to that in the end here. Here's our other implementation. This is the connected memory version. In this case, this is something that looks like a linked list. And the green up there says this is a singly linked list, and that's sufficient. So here I've got a head pointer that's pointing to my first node, and each one of these nodes points to the next node. This is a sort of simplified version of that node. We've got 4 items in there, and the last one is pointing to a null pointer to say that we don't have anything following it. We're also, in this case, keeping track of the size as a separate member so that I can look at that and say I know what the size is. So in this case, it'll be important to maintain that size so that it isn't invariant on the number of items I actually do have in the container. So here are the 5 methods: push, pop, top, size, and empty. Now how do I do this with my connected memory implementation? For push, I'm going to insert something new at the head pointer. So you can think of my oldest item as being the one that's pointing to null. So it started out with an empty list, it was just a null pointer. Then we got our first item, that purple one, it's pointing at null pointer. The second item, the blue one, was pointing at the purple one. The third item, the green one, was pointing at the blue one. And the fourth item, the red one, was pointing at the green one. Now, if I'm going to insert some 5th item, I'm going to point at the red item. So I insert the new node at head pointer and, of course, increment the size so that my size is always correct. To pop, I just need to delete the node at head pointer and decrement the size. That's pretty straightforward. However, both of those kind of gloss over the fact that I need to maintain connections here. So when I insert the new node at the head pointer, I also need the new node to point to the whatever head pointer was pointing at previously. In this case, my new node gets pointed at by head pointer, and the new node points at the red node. Same thing is true, I have to maintain the rest of my list, so when it comes time to delete, I don't just delete the node at the head pointer. I need to make sure that the head pointer is pointing at whatever that node was pointing at before. So in this case, I want to point the head pointer at the green node and then delete that red node. To get the object at the top, it's really the front of this list, right? So in this case, when I go to get the object at the top, all I have to do is dereference the head pointer. It's pointing at it. To check the size, I can just return whatever is in that size value, and as long as every time I push, I add, and every time I pop, I decrement, my size should be correct. Empty, I've got a couple of different ways I can do this. I can check to see if the head pointer is a null pointer. In this case, the head pointer is pointing at nothing. I can say it's definitely empty. Or if I wanted to use my size member and I initialized it to be 0 when I created the list, then returning whether or not size equals 0 is the same as doing empty. An alternative approach down here says we can eliminate the size member and just count the nodes each time. So we'll think about how that might work in terms of performance and complexity of operation. The green question at the bottom again, how many steps or operations are involved in each of these methods? And then our comparison as we look at implementing with connected versus implementing with contiguous, which one is more efficient for using a stack? So here's my side-by-side. When I was pushing with my array or vector version, I said it was constant because I was already pointing at where I was trying to write with my top pointer. But if I needed some more space, I would have to make new memory and copy all of my old items over there. So I can say that behavior then push with the array or vector implementation is constant. or sometimes linear. There's a little asterisk there that says this averages out to a constant over many pushes. And this is amortized constant, which is a concept that we'll definitely cover. So this would be constant most of the time and then linear every once in a while. So we'll call that amortized constant. It feels like it's constant over a bunch of pushes. Then I've got pop, which is a constant amount of work. I just have to decrement that pointer. Object at the top, just -1 and dereference. That was constant amount of time. Size is constant. Empty is constant. If I move over to the other side on the linked list, I see that that's just plain constant, not amortized constant now. It's always constant when pushing. It's always constant with popping, topping. It's constant if I track my size with that size member. If I don't track the size with a size member, I could then, every time someone asks for size, start at the beginning and next, till I got to the end. Say that's how many are in there. So if I did that, it would be linear. However, it's easy enough to just store that member side on the side there and then use that as a constant time. And then lastly, I've got this empty check on the linked list, which is also constant. So if you look at these side by side, I see that this array vector looks mostly constant, except for that amortized beginning. And then the linked list is always constant. You might think that it's a toss-up. Maybe the linked list sounds a little better. The asymptotic complexities of each are pretty much the same. They're almost all constant. However, it turns out that the constant factor attached to the complexities is a little bit lower for the vector, meaning that if I had something that said this is a constant amount of time, if I think of 5, that's a constant amount of time, versus 50, also a constant amount of time. Which would you prefer? The one that takes 5 milliseconds or the one that takes 50 milliseconds? They're both constant, so they are asymptotically similar, but in performance terms, one is definitely faster. And that's what we see most often because of the contiguous nature and the way that data is managed in the actual hardware. We find out that the constant factor attached to these array things is faster than most of the ones attached to the linked list. So we will be looking at linked lists as our last resort in 281. So if you think you should use a linked list for anything that you do here in 281, go back and think about it again. I'm not saying linked lists are always bad, but I'm saying that generally they're bad in 281. There's usually a better thing that we can do. So the linked list always allocating nodes, always deallocating nodes. So there's memory operations that happen every time we're inserting or deleting, which doesn't necessarily happen with our vector. And memory is a lot slower than just computation. So, all right, there's also higher memory overhead with our linked list. Every node has a pointer. So if we have a 64-bit machine and there's 8 bytes per pointer, every node has an additional 8 bytes of memory overhead in addition to the data itself. Here's the STL stack. The STL stack, I can get that by including stack. If you want to, you can choose the underlying container. By default, the stack is going to use a Deque. So we think of the stack class as really being an adapter. The adapter adapts what a Deque is, because the Deque is a double-ended queue. We'll be talking about that one more later. But by default, when I make a stack, it's made out of a Deque. I can optionally choose to make a stack out of a list or a vector, and STL's standard list is a doubly linked list, and that vector is, of course, the thing that is most array-like if you think of C-style coding there. So the vector is contiguous memory, as well as the Deque being contiguous memory, or mostly contiguous, whereas the list is definitely connected memory. So we can implement stacks with any of these. If you just ask for a standard stack, you'll get a Deque version. If you want to make one out of a list or a vector for some other reasons, you can ask for a stack in a particular way. That's our top on stacks. We talk about the abstract data type, the behaviors we expect to see out of any given stack, and then how it might be implemented in memory and in code. Our next basic container is the queue. We will be talking about its abstract data type and data structure implementation, just as we did the stack. So there's a slight difference from the stack to the queue. The queue has this insertion and removal in, first out order. We call that FIFO order. So that first in, first out is another thing that folks that come from different countries are much more used to seeing. We do have the concept of queues here in the States, but most of the time if you ask somebody where they're standing as they're trying to get food, they say they're in the lunch line. Whereas if you go over to the UK, they'll say they were standing on the queue at the bank. We would be standing in line at the bank. So they have that same behavior there. The first person that walks into the bank is the first person that gets served, and therefore the first person that's out of the bank. So that's what first in, first out is. That's something that we're very also familiar with. If you're waiting for something, the first person to get there is the first person to get served. And the later you show up, the later you get service. So we've got 5 similar methods to the stack here. We've got the ability to add something, which we call push again. Pop is the way that we remove things. Front now instead of top. Front is how we access an item that's in the queue. So once we put it in there with push, if we want to ever see it again, we're going to have to use front to get it. Pop doesn't show it to us. Pop just removes it. So front is going to give us a chance to see it, whether we want to just access it or if we want to modify it. We're going to have to use something that gives us access to that front there. So it's important to note that in both this stack and the queue, we've got some limitation on how the data can be accessed. When we were talking the stack, if I pushed 5 things in there, I couldn't access the first 4. I could only access the one at the top. The same thing is true here when I say I'm going to be able to access the front of the queue. If I've pushed 10 things in the line, I can't access anything from 2 through 10. I can only access the first one inserted. So that's what's important there. We've got some restriction on what's available there. And that's kind of an implementation here. Here, the ADT just says that I need access to the front. I need to have access to the front. So that's why it's important to do that. And there might be the protection on there because you might not want someone to pull somebody out of line, for instance. That might be a bad thing that could cause problems. And so your actual implementation may prevent access or modification to anything other than the front item. All the abstract data type says is we have to provide access to the front. And we're supposed to be doing this in first out order. So it's giving you this guarantee that, say, if you put this in here, it's going to come out in that order. All right, size and empty, those are pretty straightforward and very similar to the stack. We won't go into that too much. Some examples, of course, waiting in line for lunch or waiting on the lunch queue, if you will. Adding songs to the end of a playlist. You say play this next. It keeps adding things on, so you do a bunch of play next. It still puts the most recent one last, and the oldest one is the one that's going to be actually played next. Here's how we might implement this queue in contiguous memory. Now, this is called a circular buffer, and it leads to dozens of questions every time we do this. So I'm going to try to clear this up as I can beforehand. The circular buffer is important for one thing only: contiguous implementation of a queue. Okay? Because if we look at the way that a queue works, we put things in one end and we remove them from the other end. So I guess I should say this is where I think of as the back and this is the front. So as I put things in here, they go there. And so if you were to say, well, if I've got more items, they would have to be inserted farther over here and farther over here and farther over here. That's where the back is. And then as I get all the way to the front and I pull things out, now the back is right here. So I can insert things here. As I get to the front, things keep going on there. So the reason why I need a circular buffer is with a stack, I have a baseline, I add, remove, add, remove. The base of the stack stays consistent. Add, move. Whereas when I've got a list, I'll say, well, here's where the list the queue starts here, We add some things, remove some stuff. Add, remove, add, remove. After a bunch of adds and removes, I'm way over here. So I'm off my memory footprint, and that's why the need for the circular buffer with queuing happens. Because I'm putting on one end and removing from another end, I have this concept of sort of needing to get back to memory that I already used and is available. Another way to think about this is, how do restaurants work? You go to a restaurant that has 10 tables in it. Does that mean that they can only serve 10 people in a day? No. What they do is they put people in tables, and as the tables become available, they put more people in those earlier tables. Imagine if there was a restaurant that every table had to be put in, every patron had to be seated at a new table that was never used by another patron, and every day they would have to build new tables and they had to build new restaurant, even though the earlier used tables were now available. So that's how circular buffers are going to work. They're going to try to reuse the space. And so as I add to things here and I remove from them there, the circular nature is when I get to the end, I can keep adding things back over here, and then I can remove them until I catch up, and I can add more, remove, wrap around, add more, remove, and so on. So that's what our circular buffer is going to do here. One way to do this with contiguous memory is if I keep track of my front index and my back index. And I've also got a size memory to tell me that I've got sort of this capacity 3, I can see the 3 squares there, and size 0 because they're all empty. My event sequence here starts at number 1. Since the back index is equal to the front index, I will say that the array is empty. All right. As I go to push an element, I simply write at the back, because you always come to the back of the line, and then we increment that back index. Now I'm always ready, just like I was in my stack. I have one pointer that I'm always ready to just write at. If somebody says, here's new data, I just stick it in at the top pointer on a stack. I just stick it in at the back index of my queue, because the back index is waiting for data. So it's never pointing at good data, it's pointing just past good data. When I'm ready to read, that front index is always pointing at the front item. So if I insert something else here, we've put this blue element in with a push. Now I see that the back index is still ready for new data, and the front index is still pointing at the first item. I have, in this case, no real access to that blue element. That second element, which is between my pointers, I can access it. I've updated the size every time I've pushed, so now I've got size equal 2. And if I wanted to do pointer math and I were to subtract the front index from the back index, right now it would give me the value 2, because I haven't done any circular wrapping so far. All right. Now I push again. So I see that I've got a size of 3 in a container that's got a capacity of 3. This thing is full now. If I choose to push again, I'm going to have to allocate more space before I push. If I want to access an element, I still have access to it by dereferencing this front index pointer. So if I'm trying to push again, we see here that I've run out of size here. So in this case, we've gone to needing to push the red element. So that was the step 5 there. And since we already had three elements in a 3 capacity list, we needed some more capacity. So before we were able to do that, we went and reallocated these, we allocated 6 new memory locations. We sort of doubled the old container with twice as much memory here, and that's a design choice. We'll talk about that later, but in this case, we doubled the size of it. We copied all of those things over there. And why we had to double and copy was because when I run out of memory, I can't just allocate new memory at the end of the old memory. That's not the way memory allocation works in the computer. If you had 3 and you ran out of room and you need 6 more, it's going to give you 6 more, but they're not going to be necessarily where the old 3 were. So there definitely won't be overlapping the old 3. They're going to be in some place where there's room for 6. We copy the 1, 2, and 3 over from the old, and now I can push the 4th item in there. And this is what we end up here. I've got this now container that's got a capacity of 6, it's got a size of 4, with the first item being the green one, second blue, third brown, fourth red, and I've got room for 2 more. And you see that the back index is always pointing just past good data, so the back index is ready to write behind that red element that was just most recently pushed. When allocating memory, it says down here, it's common to double memory, and we will be talking about that when we talk about amortized complexity. But this is how pushback works in vectors. It doubles memory when it runs out of capacity. When size is equal to capacity, when I have as many items in the container as the container can hold, we call it full. And if we need to add more, then we go double the space and get more. Here's our first pop. And you see, all we have to do for pop is to increment my front index. So as I increment the front index, it pushes me past my original green element. In this case, we've destructed that, or if it was just a built-in type, we can forget it. But now I don't have access to that anymore. And you see that there are 3 items now in this container of size 6 capacity. I think of the first one as being unused. Then I've got blue, brown, red, and then 2 more unused items. If I continue to pop, I'll continue to move that front index forward until it reaches the back index, in which case I will say my container is empty again. If I continue to push, now since I have 3 items in a 6 size or 6 capacity container, I can push 3 more items. Where do they get pushed? They get pushed into position 4, or index 4. They get then pushed into index 5, and if I have to add 1 more, the circular nature comes in because my back index increments to hold something at 4, it increments to hold something at 5, and then it wraps around so that it can increment and insert something at index 0. So that's what the circular nature is. And then if I were to continue to pop things, I can move front around, front can hit the end, and continue to follow back as back goes, and front follows, back hits, wraps, front follows, wraps, and so on. So that's what the circular nature is. And this keeps us from having to allocate more memory even though our queue isn't at capacity. Because if I wasn't using the circular buffer, it would sort of snake its way through memory, constantly moving its front and its back and its front and its back through all of memory. And so this is why we use the circular buffer. As I pop an element there, the blue item is removed. Now I've got a size 2 capacity 4, and this is how my contiguous implementation of a queue could work. So I look at each one of these methods. I see here that I've got push. If size is equal to capacity, now I know that I need more memory, so I'm going to reallocate a larger array, copy over the old elements, and I can say that I'm going to unroll these. And this is important, where as after a collection of pushes and pops and pushes and pops and pushes and pops, in what order, I'm not necessarily guaranteed that my front index is going to be at 0. I could have popped quite a few things and pushed a few things and popped and pushed and popped, and now when I get to full, my front index is somewhere in the middle pointing at the back index. So it's still full, wrapping around full, but now you can see that the data would be sort of rolled up. And so if I'm going to reallocate, I would start from the new, start putting the data in the new container and unroll this so that in the new container, things would be front to back with the front at 0. So that's what we would do when we run out of space. If I haven't run out of space, it's pretty simple. Just write at back index and increment it. Increment the back index, and of course, we're always going to increment size when we push because we're keeping that size as an invariant of the number of items in the container. Pop is pretty similar to before. We've got some pointer where we're going to get information from. In this case, it's the front index. It's where the data originally got put in. It's not where the data is getting inserted, as in the stack. We use the top pointer for both of those things. Here we use the 2 pointers. The front index is what I can increment to remove something, and I also have to decrement the size, destroy the object if it's an object, and so on. Object front, all I have to do is just return a reference to the element that front index is pointing at. That's great. Size, I can return that member and empty, check to see if size is 0 or if front index is equal to back index. How many steps? What do I think that's going to be complexity-wise? How many? Here's my connected memory version of this using a linked list. I can also use this singly linked list as well. However, you see now that we've got a tail pointer. That tail pointer is always pointing at that last object, or in reality, that is the first object. It looks like the tail pointer because we're inserting at the head, but if you remember, where do you get inserted in the queue? You get inserted at the back of the queue. So we might think of that head pointer and tail pointer because it's really the head of the linked list and the tail of the linked list. It's really the head pointer is the back of the queue and the tail pointer is the front of the queue. So when I go to append, oh, I said that backwards, didn't I? I did that completely backwards. It's a different implementation. Rewind that, go over. So we're going to insert things at the tail pointer. We keep that pointer just for insertions. All right, and then the head pointer is where we're going to read from. Sorry, I got my implementation reversed. You could do it either way. So that's why you don't worry too much about that version of it. So we could be always writing at the head pointer and always removing from the tail pointer, or we could be always writing at the tail pointer and removing from the head pointer. The key to the queue is that the two behaviors happen on opposite ends of the list. And so we need to have an additional pointer there. Here we've got a tail pointer in the way we think of the linked list as the head of the linked list, the tail of the linked list. So our push is going to append after the tail pointer. So I need that I can get there in a constant amount of time. To delete at the head pointer is how I remove something with pop. In both of those cases, I'm going to increment or decrement the size so that it stays invariant on the total number of nodes that are in the list. To get the front, I'm going to dereference the head pointer. Size and empty are really straightforward. Alternative approach, I could count the nodes when I needed them. I don't have to store the size as a separate member. How many steps or operations for each one of these methods? Here's my side by side. When I push, I can think of that as being a constant amount of work when I've got the space for it in my contiguous memory. I just write and move on. When I'm out of space, my size is equal to my capacity. I've got to resize my vector and copy everything over there. So now this is linear. We call that amortized constant. It means that it feels like constant over the life of the container. But every once in a while, it's a lot slower than constant. But usually it's pretty constant. Pop is constant. Front, size, and empty are all constant. Those things are pretty straightforward. When I get to the linked list, it's similar in many ways to the way that the queue was. To push some new object, I just need the pointer to connect it to, and to create it, I can get that done in a constant amount of time. To pop, I've got a pointer pointing at the thing I want to destroy. I just destroy that and move on. Front, I've got a pointer pointing to what I need. I just dereference it, and there it is. Size and empty, I can check my members that I have. So constant, 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 and much like our connected versus contiguous argument in the stack, we're going to say that it's going to be a lot better to go with the contiguous memory version, right? Because the constant factors attached are lower for these vectors than they are for the linked list. We don't have to do any memory allocation that we have to do every time we push something into a linked list, and we don't have the memory overhead of all of those pointers. So once again here, if we're looking at how we might do this, and you're wondering, maybe I should use that linked list, think again. Use the vector. Use the contiguous memory. Much like the STL stack, I'm going to use an STL queue. I'm going to include queue. You can choose the underlying container here. However, we don't have quite as many options. The default for making a queue is the Deque, the double-ended queue. And if I want to do this optionally with a different member, I can do this with a list. I cannot do this with a vector because vectors have the problem where when you remove something from the beginning of it, we have to slide all of the things over. You remove something from the beginning, we slide things over. Remove things from the beginning, we slide things over. So it makes it could be done, but not everything that can be done should be done. And in this case, trying to remove things from the beginning of a vector would mean that every time I remove something, it would be a linear activity because I have to move all of the other items forward one to take that space out. So this is why the STL doesn't do that. It thinks of that as something that's too ridiculous to be dealt with and is not implemented there. So my default queue is made by adapting a deck. If I want to, I can specify on a special request to make my deck be implemented by adapting a doubly linked list. So that is my coverage of the queue. First in, first out container. Let's talk about our last basic container here, and that's the deck. The deck is basic in the sense that it's not customizable in the way that it works, but it is not basic in the way that it actually works. It does some pretty amazing stuff. It gives us constant time access to inserting and removing things from the front, inserting and removing things from the back, and anything in the middle. So it sounds like magic. There's got to be a reason why we don't use it for everything, because it sounds wonderful. And there is a reason why we don't use it for everything. We'll talk about it. So Deque, D-E-Q-U-E, is a made-up word. It's an abbreviation of double-ended Q, D-E-Q. So in the English language, we actually already have a word that's spelled D-E-Q-U-E-U-E. That means DQ, or to get out of line. So NQ is how you put something into line, and DQ is how you take something out of line. So DEQUEUE might be a little confusing. Therefore, this made-up word DEQUE, which is just pronounced Deque, is the thing that we've made up here. So this is the STL. You can find this in standard Deque, and you can include a Deque, and it's a great implementation of a double-ended queue. It's usually based on a growable collection of fixed size arrays. So you can think of this as kind of a vector of vectors, not in the 2D vector of vectors sense, but in the 1D vector of sense, where each of my new vectors is more of the sequence. And then I've got a vector that points to where the other portions are. They're called chunks. So Deque, D-E-Q-U-E, is something that we're going to use. It's a queue and a stack in one because it allows efficient insertion and removal from both ends. So I've got these 6 major methods: push front and pop front. That adds and removes things from the front. I've got push back and pop back, which can add and remove things from the back. And of course, front to access something here in the front, and back to access something here in the back. Minor methods, checking size and empty and the like. You can also traverse a deck with an iterator, which is really nice. We can go through all of the things in the deck. The picture here is a deck of cards, and it's very similar. We don't have anything that we can't do with a deck that we wouldn't think of being able to do with a deck of cards. I can easily put something on the top or remove a top card. I can easily put something on the bottom, or I can sort of work my way through them and look at a card somewhere there in the middle. So that's great. STL includes a constant time square brackets operator, which means I've got random access to any item inside the deck in a constant amount of time. Sounds like magic. Here's my 2 implementation styles, right? I've got contiguous memory and I've got connected memory. The circular buffer is needed here for this Deque implementation. That's one way to do it. I've got a front index and a back index, and I can constantly be adding to both ends there. So you can think of that as I run out of space here. I can push back and wrap around. So I might do this with a couple of pointers. If I've got a front index pointer and a back index pointer, I can keep adding things to the front index. I can keep removing things from the front index. I can add or remove things from the back index, and it works out by incrementing and decrementing those things. If I were to go doubly linked list now, I can't do a singly linked list here because it doesn't support efficient removal from both ends. Singly linked lists do allow me to efficiently insert from one end and efficiently remove from one end, but it doesn't allow me to do those things really easily, right? Other operations map directly to doubly linked list operations, like how do I sort of push on the front, push on the back, and so on. So we won't go into this one too much because it's done actually quite differently in the STL. So the STL, here are a couple of images of how this might get done. We've got these data chunks, and this is a collection of contiguous values. So you can think of like this is where one of these vectors of vectors are, right? Oh, I got something in my eye. And I've got this map here, which allows me to work my way through the chunks. So you can think maybe I've got 6 items here, and they go 1, 2, 3, 4, 5, 6. And I've got 6 items over here, and there's 7, 8, 9, 10, 11, 12. I got 6 items up there that are 13, 14, 15, 16, 17, 18, and so on. I need some way to reference them in order, and that's what this map is here. So this is my vector of vectors. As I'm working my way through the chunks, I can read through this map and say, first chunk, go there, get the items. Second chunk, go there, get the items. Third chunk, go there, get the items. Fourth chunk, and so on. So this is one way you can do it, and the image on the far side over there shows how the first chunk fills from back to front. And this is how we get our constant time insertion there, because as I go to insert something at the front of this, it just puts something earlier in that first chunk. The last chunk fills like you might normally expect things from the left to right. Well, the first chunk fills from right to left. So that gives me constant time insertion at the front, constant time insertion at the back. And you'll see that it takes a couple of constants or a couple of members to manage this. So we've got a chunk size, and this is how we find things. I say if I'm looking for the 15th item, then if I started with a full chunk, I would have 6. There's 6, my chunk size equals 6. I'm looking for the 15th item. I can think of 2 full chunks and then the third item in the third chunk. That would be the 15th item. No problem. However, since my first chunk isn't guaranteed to start at 0, I've got this shift member that says the first 3 are actually empty. So if I want to find the 15th, I'm going to take and add 15 to my shift. 15 plus 3, that's going to tell me I've got to look at the 18th item. Then if I take my chunk size, I can find that the 18th item should be in the third chunk at the end. And so that's how the math on a deck works. It allows you to get random access inside. It allows constant time insertion at the front and back. When we run out of space in the chunk, when we fill a chunk, we just go make a new chunk. So that's a difference between vectors and decks. When we run out of space in a vector, we got to get the whole thing moved. Whereas when we run out of space in a deck, we just got to go get a new chunk. If we run out of space in the map, as in we've got so many things that so many chunks that we're keeping track of, it's fairly easy to go get a new map and then update the map with all of the values of the previous map. So this is a couple of different ways you can look at things working inside the STL's deck. To get there, we're of course going to include Deque, Deque. It's got stack-like behavior at the front and back. It also has random access with square brackets or a function called at, which is the way that square brackets is implemented. Square brackets is really just some syntactic sugar for calling the at method. Sometimes they're implemented with the exact same code. Sometimes, depending on the compiler, they may be implemented slightly differently. For instance, I believe that during debug mode, if you use at on a deck on a Windows machine, it will actually do bounds checking and help you like that. Whereas in the GCC compiler, at and square brackets are very similar. It doesn't matter whether you're in debug mode or not. If you access outside of the thing, just bad things happen. All right, that was our last basic container. Up next, we're going to talk about a customizable container here, and this is the priority queue, heart of Project 2. So we're going to be digging into priority queues, something serious, real quick. But today we're going to talk about them. So call a priority queue a customizable container because what we're going to do with the priority queue is tell the priority queue how to determine what is important. The stack and queue were not customizable because the last item inserted was always the last item inserted. The first item inserted was always the first item inserted, and nothing could change them, and the behaviors were based on that time of insertion. Whereas in a priority queue now, we say that every item is going to be paired with some priority value. Sometimes that priority value is going to be implicit, whereas we calculate the priority from some other members that are part of the datum. Other times it will be explicit, like here's this type of call and it has priority 1. So we can have implicit or explicit values. Usually they're going to be numbers. And the reason why we say it's a customizable container is because I can say, well, when I put these in there, I want important to be the big numbers, or I want important to be the small numbers. And that can be changed on a per priority queue basis. And so that's what makes it customizable. So I can determine that when things get inserted, they come out in a different order, depending on how I want them to come out. So that's what makes the priority queue a customizable container. We would like to be able to compare our priority values. It's hard to decide which things should come out if I can't compare my priority value. So these numbers work out great, and if I can compare them with a less than, that's great. It's going to support, of course, insertion and inspection. I need to be able to put items into the priority queue. I need to be able to look at the most important item. So that's what a priority queue does. It also supports removal, and that's going to be taking out the most important item. And that's what the priority queue is good at. Most important, of course, is the customizable aspect of this. Is determined by what I decided was the ordering that mattered to me. One way to think of a priority queue is a bike race. We've got a picture of one of these here. You can think of all of the racers have been inserted into a priority queue, and then the fastest racer is the one that comes out first. And that's what the racing priority queue does, is it determines the most important racer. So that's pretty interesting there. The fastest ones exit the race first, even though they all got inserted at the same time. It's not about when they were inserted or what numbers on their jersey. It's about how fast they were in the end. So their overall speed and endurance are the important thing there. Here's an example of a priority queue. We've got an emergency call center. Operators receive calls and then they assign levels of urgency, and then we've got the ability to dispatch somebody to handle this. So the lower the number is, the more urgent your call is, as in I have 0 minutes that I can wait before I handle this. I have 0 other units I can send out before I send out a unit here. Right? There may be 1 or more units that I can send out before I handle a priority 1 call, or a priority 2 call, maybe even lower than that. So for example, here is our emergency helpline, and we've got things like a level 2 call says I have a cat stuck in the tree. All right, how about a level 1 call? A level 1 call is like, I think I heard something downstairs. And then a level 0 call is, the house is on fire. All right, you can see the changes of the various levels of priority there, right? If we've got somebody to send out, as much as we love cats, we're going to send somebody out to a fire before we send someone out to rescue a cat in a tree. All right? Same thing with the possibility of someone being downstairs. There could be someone downstairs, in which case there could be a danger to people in the house. Or, who knows, could be the cat just making some noises. But we know for a fact when the building's on fire, that's most important here. So, in this example, we've got a level 2 call comes in. Cat in a tree. Next up, we've got another level 2 call. This is another cat. It's a cat epidemic. 2 cats, 2 trees? I don't know, maybe it's just 1 tree. But both the cats are stuck. We haven't sent anyone out yet, so if we get someone to send out right now, we're gonna go send them to rescue a cat. However, we've got a level 1 call in. I think there's somebody downstairs. All right. Now, if we've got someone to dispatch, I'm going to send someone there. There's much more chance of harm coming from an intruder than there is from a cat, which, let's be honest, they can climb down trees too. All right, so we dispatch someone to handle a call. Because of that priority queue nature, we're going to send someone to the level 1 call. All right, next up, we've got a house on fire. That call comes in. That's now in my 0 priority level. If I've got a dispatch, that one's going straight to the fire. The cats are still going to have to wait. Sorry, buddy. All right, I got a call that gets dispatched. We take that 0 level and we make things go. All right, so that's the priority queue example. In this case, we've got explicit priorities. The call is separate from its priority. We've attached a priority to it, and then we put them into the container, and the container tells us which order things should come out in. Here's my priority queue ADT, the interface. I've got 5 methods again. Well, these containers are all fairly simple. We like to add things, we like to remove things, we like to look at something important, and then we like to check to see if it's size and empty. So we'll call these push and pop again. Now we're gonna go with another top member, just like we did with a stack, but the top is not the most recent item. The top is the best item, the most important item. The priority queue is about attaching importance and returning importance. So however the user defines importance, that's what it's going to do. Push just adds an object to the priority queue. Pop is going to remove the highest priority element, and top gives us access to the highest priority element. You see here, this one is const because we don't want to be able to change the priority of an element in the priority queue. We only have access to one at the top, but if someone were to change that priority and say, for instance, lower the priority so low that some other item in the container should be at the top, that could cause problems, which is why we've got a const reference to that object on the top, because we don't want changes that could affect the priority of the object. Other changes, actually kind of okay. You have to be careful about that though. So we'll start out by looking at these as just const and const only. So some examples are, of course, a hospital queue for arriving patients. You come in, first come, first served. That's what you think of at the bank, but you don't want someone that's bleeding there waiting for someone to have a headache dealt with just because the person with a headache showed up before the car accident. So the arriving patient that's most important is the one that gets dealt with soonest. Load balancing on servers also works in a similar way. So it doesn't matter how long the request was in there, the most important requests that need to get handled. We get those balanced out so that we can handle more important items before the less important items. We can, of course, implement this a couple of different ways, more than a few different ways. We're going to be doing this 3 or 4 different ways in project 2. So I've got the 2 primary behaviors there, insert and remove, and then I've got an unordered sequence container. That means I don't care what order they are in, I just keep them in there. So in that case, I can just take something new and just insert it anywhere at the back. There's space there, I'll put it there. So I can put that in there in constant time. However, to find the most important item when it's unordered, I have to go look through all of them and figure out which one is most important, then I can remove that. So I can't do that without looking at all of them. I'm going to say that removal is now linear behavior with an unordered sequence container. And we're going to provide you an unordered sequence implementation for your PQs to look at as an example. Another way I could do it is say, well, if I didn't know where it was because it was unordered, what if I kept things ordered? What if I sorted them? That would be great, because then I would know where the most important thing was all the time, and my removal would be constant time. However, inserting something into a sorted container is not constant time, right? I've got to find out where it belongs, which if I'm slick, I can get that done in logarithmic time. I can figure out where it belongs. However, when I go to insert something in a sorted sequence, I have to move the other things out of the way if we're talking contiguous memory. So I might have to sort of move them out of the way. You say, well, what if I use the linked list? Well, I would say bad. But the thing about the linked list is now I can insert that physically in a constant amount of time, but I can't do the logarithmic find of where to insert it. I have to do a linear search to figure out where to insert it. So in either the contiguous or the connected method, I still am going to be looking at a linear insertion time, even though now I can do my removal in constant time. So you can see that unordered and sorted are kind of like flip-flops of the same thing. One is really quick with one operation and slow with the other, and vice versa. What about a heap? We'll be talking about that more later. Heaps are great for priority queue implementations because they give me a logarithmic insertion time and a logarithmic removal time. So the net combination of all of my operations stays in that logarithmic range, which is going to be better than the linear that I would get with either of these two. So another way that I can do it, and you saw my earlier method there when I did that example with the kittens and the fire. We've got this array of linked lists, and this is where I've got small integers for my priorities. So I've got a constant list of priorities. I can do that in a constant amount of time for insertion and removal, and that works out fine. Because there, it doesn't matter where I insert something into the level 2. If they're all level 2s, any level 2 is as good as any level 2, so I don't care if this level 2 got here before that level 2, they're actually the same. If I wanted to have some other way to distinguish between those priorities, then any two level 2s are not the same. If I wanted to put a temporal thing on there, that's just a little bit different. So the way that previous example was is whatever happens in the 2 queue, or in the 2 collection, doesn't matter. Any one of those that comes out is as equal as any of the other ones. So here we've got an example of that one. This was our array of linked lists. And you can see how I can just access my most important priority and go pull that out. Even if I have to do sort of a linear search through my priorities to figure out who has something in that list. Does a 0 have an item? Does a 1 have an item? Does a 2 have an item? Does a 3 have an item? Doesn't matter. I've got a constant number of priorities, so accessing the list that has elements in it is still a constant amount of work, right? The part of this that is the N is how long do things go in those linked lists. That's where N happens. So looking at one of the 3 or 4 or 15 priorities, who knows how many different levels of priorities you have, as long as there is a constant number of priorities, finding the most important item to handle is still a constant amount of work. Even if I look through all of those different priorities and find, oh, here's the list that has something in it, I'm going to give you the first thing from that list, also a constant amount of time. So that's why we can say that for an array of linked lists, I can call this a constant insertion and a constant removal. But that's a special case. We can't always use that because we can't always predefine all of our priority levels. For instance, if you're working with zombies in a project 2, for instance, you might be concerned about how soon the zombie is going to get to you before it eats brains. So some zombies might arrive in 50 rounds or 5,000 rounds. There's not a fixed number of priorities there, so we can't use this array of linked lists version of it because we might have too many linked lists to get there. So customizable container, let's talk a little bit more about that. I'm going to try to get to these permutations quickly. I'm running out of time here. Customizable container. By default, a standard priority queue uses standard less to determine the relative priority of 2 items. Look at this. Is this thing less important than that? Great. I'm going to put this more important thing closer to the top. So the standard priority queue has a choice. It can look at 2 items and decide which one to make the most important one. And this is an arbitrary choice that the authors chose. The standard priority queue could have said, I want to use greater. And then it could have worked just as well. But the way that it works is standard priority queue uses standard less. And that gives us the way that we think priority queue should work. And if I were to ask you what's most important, most people think of the big numbers as being important. And that's how it works. So standard priority queue using standard less gives the biggest element out. That's the way it works. That's something that is a fact that you have to remember. This is like history. It just happens that way, so you have to remember it. So that's something you have to put together in your head. The same way that I say if I want to sort things, if I use standard less, it's going to give me an increasing list of items. So that's a choice that the authors made at the beginning of the STL. Standard priority queue with standard less gives me what we call a max priority queue, because the thing that's the maximum element, the most important thing, is the maximum element. And standard less gives us the maximum element. That's the part that you have to remember. So the default priority queue, the one we think of, is the max PQ. Largest element has the highest priority. If we want a min PQ, remember, a min PQ is not the least important item. What a min PQ is the most important item, is the smallest. So if a min PQ is desired, then we swap the creation of the priority queues from standard less to standard greater, or some function that behaves like a greater than. Then I end up with the smallest value element being the one that has the highest priority, because the priority queue always gives you the highest priority. Min PQ does not mean minimum priority, it means the maximum priority is the smallest element. If the PQ can hold elements that can't be compared with standard less or standard greater, then you have to add your own functor. You have to add this, what we call a comparator, which is a function object that takes two items and returns true or false. True or false, are they in the correct order? And then something happens as the priority queue manages things. So custom comparators can work with objects. They can do tie breaks on multiple members, and there's lots of things that custom comparators can do. So this is where we talk about the customizable nature of a priority queue. So here's standard priority queue. It isn't include priority queue. It actually just lives inside queue. So if you would like to get a standard priority queue, just have to include queue, and then you would have to be either using namespace standard or be using standard priority queue. Standard priority queue, we can look at some simple declarations here. If I say standard priority queue of T, then that means that I'm putting some T's into this thing, and it's going to give me the T that has the largest thing in there when I call it out, because less can work on T's. If I want to use a custom comparator type, I've got to use this second version of it where it's priority queue, type of thing in priority queue, vector of type of thing in priority queue, because it's saying that we're going to make a priority queue that holds T's, and the method and the container that holds them is going to be a vector of T's. So it's important you have to have the second parameter in there, because that second parameter allows us to put the comparator in the third parameter slot. So it's unfortunate that that's the way it works, but it's consistent with the way that the STL works, in the fact that we say that if I've got some container that's got some things in it and I want to control how it gets created, the second parameter is always the chosen container type. So in this case, the priority queue of T's in a vector of T's, and then the comparator allows me to add my own custom comparator. So you have to do that with 3 values there. And this is a description of a type. So the things in T, vector of T, and comp all have to be types, not objects, types. There's a distinction there. We don't want to create an object in my type definition. I only want to put types in there, and then the variable that I get out of it is going to be an actual object. Other ways that I can implement a priority queue, there are some functions in the STL that do this. If you include algorithm, you can call functions like make heap, which creates a heap out of not heaped items, and then they can perform like a priority queue. Push heap adds things, and pop heap removes things. So if you want to make your own priority queue, the STL priority queue actually just calls these 3 functions. So feel free to do that if you wanted to make your own customized priority queue. That is talk on priority queue. I'm down to short minutes here, and I've got just a little bit of time to talk about generating permutations. So in this example, we're going to be talking about juggling. That's what the picture shows. And we're going to be juggling with stacks and queues. So really, we've got some number of elements. We're never adding an element, and we're never getting rid of any elements. That's why the juggling metaphor is apt here. But we want them to be in different orders. So the task is, given these n elements, generate all n element permutations. So if I've given you 3 elements, I want you to give me all of the orders that those 3 elements could come in. And where we're going to get this done is with a recursive function, something that works like a stack, and something that works like a queue. And the technique is it moves things back and forth from one container to the other, hence the juggling. So for example, if the input is 1, 2, 3, and I want the permutations of that, it might give me all of these things back out. The set that has 1, 2, 3 in it, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, and 3, 2, 1. Those are all 6 ways that I can permute 3 items. Gen perms would take this as input and shoot out all of those as its outputs. Here's a helper function to make sure that we know this stuff works, and I can get this done by printing them out. That's one way to do it. So all this does is it makes a nice overloaded operator stream insertion operator. So that's operator less than, and I give it an output stream, and I give it a stack, and it prints all the items in a stack. Well, wait a minute, the stack only has access to the things that are at the top. How do I print all of the other things in a stack? And you can't without destroying the stack or without destroying a stack. So this version of it says, let's make a copy of stack, and then as long as this copy isn't empty, I'll pop things out and print them, pop and print, pop and print. So I can use this to print a stack, but I have to do this with a full copy. So might not be the best way to do this. Another way to do this is say, hey, well, instead of using an actual stack, what if I just used a vector? Because a vector, remember, can give me stack-like behavior. Vector has pushback and vector has popback. And I can use that to implement a stack, right? So if I say I'm going to implement my stack with a vector, now my better helper function says I don't even need to make a copy, which takes a linear amount of time. I can just work my way through each one of those items in the vector and print them out. And if those things happen to be objects, I want to make sure that I'm going to use this auto L by reference so that I'm not making copies of objects just to print them. So there's my helper function. I'm going to use this later for figuring out what is in my stack. Here's my implementation. We see we've got a stack and a queue. Remember I said that earlier, we're going to use a stack and a queue. But if I look at the parameters here in gen perms, it takes a vector of t's and a deque of t's. Well, that is really a stack. That perm is in a vector, but if you look at the way that perm gets used down below, in line 9 we're doing pushback on the perm. In line 12 we're doing perm.back, and in line 13 we're doing perm.popback. So we're pushing and accessing and popping from the same end. That's what a stack is. Unused, of course, I say that's a deque here in this declaration, but it's going to actually be behaving like a queue, because if we look at the way unused works, we've got a front in line 9, we've got a pop front in line 10, and then we've got a push back in line 12. So we've got things coming from here and going in there. So that is my queue-like behavior. So you can think of perm as being a stack, and you can think of unused as being a queue. The only reason that we've done them in vector and deque is because it's easier later to be able to print all of the items in a vector. But other than that, they're behaving exactly like those stacks and queues. So in gen perms, what we're doing is we say we've got this list of permutations, and I've got a list of unused items. I'm going to keep moving things from the unused hand into the permutation hand, and as soon as the permutation hand is full, because the unused hand is empty, this is a permutation. Let's print it. That's what my base case is here, lines 4 through 5. I say base case because gen perms defined in line 2 calls gen perms in line 11. This is a recursive function. Recursive functions can't exist without the base case. So all about that base, we got to get out with a base case. All right. If unused is empty, then we're going to do something and quit. There's my return statement in line 6. If unused is empty, everything is in the permutation, so we're just gonna, for this one, we're just printing it. If you were doing something else, you might do something special here in line 5 with a full permutation. Lines 8 through 13 are how we generate this permutation. So when we start out, everything is unused and nothing is in the permutation. Every time we move into gen perms here with another call, it's because we've added something new to the permutation. That's in perm pushback, line 9, and we've removed it from unused, which is lines 9 and 10, where we look at that thing from the front and then we remove it from the front on unused pop front in line 10 there. Then we put it back at the end after we've done our gen perms again. So we'll take that thing back off of the unused, or sorry, back off of perm back and stick it back into the other end of unused. So in this way, everything in unused gets it's shot one at a time because it's a queue. They keep coming from the front and going back in the back, whereas we keep putting things into the back of the perm and then keep popping them off the back like that. So that's what we got. So we kind of do some work with lines 9 and 10. We call gen perms, and then we undo the work in lines 12 and 13. When we call gen perms, it's important to note that perm is one longer than it used to be, and unused is one shorter. And you can see that in line 9s and 10. Line 9 does a pushback onto perm and a pop from unused, so unused is one shorter, and that item has not been lost or destroyed, it's been put into perm. And then when I come back, I take that item back out of perm and stick it back into unused. So every time I call gen perms here, the permutation length is growing and the items that are unused are shrinking. When I've got nothing unused, I've got a full permutation, base case print. That is gen perms. A slightly faster version of this, I'll show you that in a minute, but this is just a sample driver that asks you for a number of items, then creates a list of those items, and then prints all of those things out. Right? Yeah, that's good. One question here, how does gen perms compare to the STL's function next permutation? Because you would think something like that would be something that the library might have, and you'd be right. There is a next permutation function, which is a reentrant function that allows you to keep calling next permutation and get a permutation off of this thing. However, next permutation generates every single permutation. It does it really well. If I wanted to maybe skip some permutations, I wouldn't be able to do that because next permutation has to go through them all. Gen perms being our own will allow us to sort of say, hey, this is a really bad start. Say there's this factorial permutation. So if I've got 15 values and I'm trying to figure out all 15 factorial permutations, maybe my application says, well, these first 3 are a really bad way to start. We don't even want to go past these first 3. With next permutation, I'd still have to generate the 12 factorial remaining versions that started with that bad 3. Whereas with gen perms, I might be able to say, well, these 3 are a bad start. Just skip all 12 factorial things that continue that. And you get a lot of speed out of that. So there's some things going on there. This is my other implementation. Make sure you understand how gen perms work. If not now, you will have to use it for project 4. So we're giving all kind of big ups to upcoming projects. We talked about priority queues, that's all of 2. We've talked about gen perms, which is the heart of 4. This implementation does exactly the same thing that the previous version does, but in one container now. Now instead of having a deck and vector, we've just got one vector, and we kind of move things around in there with these calls to swap, and everything that swap does in line 10, swap undoes in line 12. And line 11 just calls gen perms with more items. So gen perms is not going to be something that we're going to test you on. It's going to be something that you have to know and be able to use in P4. That's more than enough. All right, that is my day. I'm sorry that I got over time here, but I've had a good time here on the road from my hotel room. I will be back here tomorrow and then back in the Ann Arbor front next week. That's time. Give it to him, P. Have a good one.